Today in class we are starting a new chapter, and as part of our calculations we do need to remind ourselves how to convert degrees to radians, which we've already done in class before. So I just wanted to remind you of our little formula that we had, which was if you want to know the radians, you take your degrees and you multiply by pi over 180. And then essentially that turns into a fraction, which is just d times pi over 180. And then you reduce the fraction. Let me give you a quick example. Let's say we want to convert 330 degrees. We would take that 330, multiply by pi and divide by 180. And then if we want the radian measure in terms of pi, we have to reduce this fraction, which really means we're going to reduce the 330 over 180. So the quick way to do that, well, there's nothing quick about reducing fractions, but one quick way is, first of all, you can see that they both reduce by dividing by 10, so we can cross out these zeros. And then 3 will go into 33, and 3 will go into 18, and that makes 11 and 6. And so this 330 pi over 180 actually reduces to 11 pi over 6. That's the radian measure for an angle of 330 degrees. And you can check your unit circle. 330 degrees is on there, and the corresponding radian angle measure is 11 pi over 6. So this formula does work. Now we're going to need this formula throughout our problems today when we compute arc length and sector area, because both of those formulas require a central angle that is measured in radians. So radians are kind of a big deal for the lesson. And that's why we needed to run through this little reminder of how to convert degrees to radians. So let's move on to arc length, and we'll talk about what that's all about. So when we do arc length problems, what we're really trying to do is measure a little piece of a circle. So here's a circle, and an arc is just one piece of that circle. So this little red drawing here, that's really the arc. And what it is it's the piece of the circle that's knocked out when you draw an angle. And this angle here is drawn at the with this vertex at the center of the circle, and that's called a central angle. So when the angle is drawn with its vertex on the center of the circle, that's a central angle. We are going to use the symbol theta to represent the central angle. And then the arc that's cut by that central angle, this red piece here, is being labeled with letter S. So the variable S stands for the length of that little arc. And the deal is that we just realized this is a percentage of the entire circumference of the circle. It's a fraction of the entire circumference of the circle, and when you set that proportion up and solve for S, what you get is a very simple formula. Our arc length formula is S equals the radius times the central angle. S equals r theta. That's our formula. And what I tell students is to remember the phrase radius times radians. And that reminds you of a couple things. Number one, you're going to multiply the radius by the central angle. And number two, that central angle needs to be in radian measure, not degree measure. It needs to be in radians. For example, let's find out the arc length for a central angle that's measuring 128 degrees, and the circle has a radius of 5. So the central angle is 128 degrees, and the radius is 5. If I'm going to compute this arc length S, I'm going to write down the radius, which is 5, and I'm going to multiply by the radian equivalent of 128 degrees. And remember, we just reviewed how to convert that. That's just 128 pi divided by 180. And truthfully, I'm not really concerned with how that fraction reduces because I'm going to write my arc length as a decimal number anyway. So your job is simply to multiply this out, 5 times 128 times pi divided by 180, and discover that that works out to be approximately 11.2 centimeters. Now, I didn't mention this, but this radius is measured in centimeters. And so my arc length is also measured in centimeters. Just realize that arc length is measured in the same linear units that a radius is measured. And so whatever the units are for the radius, that's what you're going to use for the arc length. I did radius times radians, cranked it out on my calculator, came out to 11.2 centimeters. And that's all it is for arc length. Radius times radians. Just make sure that your angle is measured in radians before you multiply. Let's talk about sector area before we get into a few other miscellaneous problems. So a sector is just one little pizza slice of a circle. So if I draw a central angle, instead of just thinking about the crust or the little side arc that it cuts, I think about the entire area inside that angle up to the circle. That's called a sector. Still have a central angle, but the sector is this entire shaded region here, not just the arc that's cut, right? Last discussion was just about that arc there, but the sector is the entire region here, and we're trying to find the area of that region. You can think of it as a triangle with one curvy edge. Well, just like the arc length problem, it's really just a proportion or a percentage of the full circle. And you know, we know how to do the area of a circle with pi r squared. You set up a proportion and you solve for the area of the sector and you come up with the following formula. And this is the formula that we'll use whenever we do sector area. That formula is A equals 1/2 times r squared times theta. And just like the arc length formula, theta needs to be measured in radians. Okay, so when you have that central angle, make sure it's in radian measure. And here's a quick example. Let's say I want to know the area of a sector that's cut by a central angle, which is 5 pi over 6, and the radius of the circle is 16 centimeters. If you want to figure out the area of that sector, you simply write out A equals 1/2 times 16 squared times 5 pi over 6. And again, because we want to represent this area as simply a decimal number so that people can make sense of how big that sector really is, we are simply going to type in 1/2 times 16 squared times 5 times pi over 6 times pi divided by 6. And when you do that, you're going to get an approximate area of about 335.1 square centimeters. If your radius is measured in centimeters, your sector area is measured in square centimeters. So make sure you label those answers. But in a nutshell, that's the sector area. So we're really just using this formula and filling in the radius and the central angle in radians and cranking it out on our calculator. These problems are pretty straightforward. Now things do get a little more interesting, and I want to give you two other quick examples before we wrap up the video. In class, we worked out this geography example, and we're told that Winnipeg, which is in Manitoba, Canada, and Dallas, Texas, lie on the same longitude line, 97 degrees west. So essentially, Winnipeg is directly north of Dallas on the map, or on the globe, I should say. And then we're told that the latitude for Winnipeg is 50 degrees north and the latitude of Dallas is 33 degrees north. We're also told that the radius of the Earth is approximately 3,960 miles. Our job is to find the approximate distance between the two cities. And sometimes you have to draw your own picture for a story, but in this case, they've drawn a picture for us. This is a cross-section of the globe. And you know, hopefully, that latitude is measured from the equator. So 50 degrees north of the equator is the city of Dallas. Or excuse me, 33 degrees north of the equator is Dallas, and then 50 degrees north of the equator is Winnipeg. And our job is to find out how far apart these two cities are. So we're trying to find this arc length. That's not a 5, that's an S. Trying to find that arc length. So remember that to do arc length, it's just S equals the radius times the angle, and it has to be in radians. Well, I don't even have an angle yet. I have to figure out what the measurement of that angle is right there. That's theta, that little one in there. So for starters, I'm going to calculate that as 50 minus 33, right? The difference between Winnipeg and Dallas is 50 minus 33, which is 17 degrees. So if I want to find that arc length, I'm going to do the radius, which is 3960, times the angle 17 written in radians, which is 17 pi over 180. And when you crank that out, you get the value for the distance between those cities. I'm just going to round that off to the nearest mile. And when I type that in, I get 1,175. And that's in miles. Remember, arc length is measured in the same units as the radius. So those cities are approximately 1,175 miles apart based on the information we've been given in this problem. This is really just an arc length problem. So we use the arc length formula. I've got one last little example, and then we'll let you go for this video. An arc is measured 14.2 centimeters long and is intercepted by a central angle of 60 degrees. What is the radius of the circle? So if I'm drawing a picture of this thing, I have a 60-degree angle, which we know looks approximately like that. And I know that the arc length is 14.2 centimeters. This was 60 degrees. What I want to know is what in the world is the radius, right? That's the thing we're trying to find out. What does R equal? Well, the only thing I've taught you about arc length is that the arc length S equals the radius times the degrees in radians. And that's all you have. So we're going to use this equation and we're going to fill in what we know. I know that the arc length is 14.2, so I'll write that in place of S. I don't know the radius, so I'm going to leave my variable R there. But I do know the angle. The angle is 60 pi over 180. And 60 pi over 180 actually reduces to pi over 3. So to make my life easier when I do this calculation, I'm going to convert that ahead of time. So my equation is 14.2 equals pi over 3r. Or if you prefer, we can do pi over 3r equals 14.2. And then our job is to divide both sides by pi over 3. Or multiply by 3 over pi if you prefer. And you can go ahead and, again, since we're doing a radius measurement, we want just a decimal value. If you crank this out on your calculator, you're going to find that this is approximately 13.6, and that is also centimeters. Remember, if the arc length is in centimeters, then the radius is in centimeters as well. So that radius happens to be 13.6, and it makes sense that it's a little bit smaller than the arc length because we multiplied the radius by a number bigger than 1, so it grew a little bit to get the arc length. Okay, so we've shown you several examples of these calculations. Give the problems a try and see how you do, and let me know if you have any issues. Take care.